So the relationship between critical stress and slenderness ratio is actually this. And you can move this thing to here. And rewrite it again. And we're going to have sigma CR as a function of slenderness ratio to be what? To be just expression over there. Confidence pi squared times E and times L over R to the power of what? -2. So this is how we got this curve. So this curve is theoretically derived. It's not just experimentally obtained. Experimentally, we obtain those points. This curve is theoretically derived, which is for this curve here. Right? Now, I also talk about that when we consider the yielding, right? When we consider short columns and long columns, and that means somewhere here there's a yield stress, sigma y, and from here you can draw the line so that this point is going to be yielding. Now for real structures, this is the region where stable behavior can be expected, which is this region. Because in this region, which is right here, in this region, above PCR, there's what we call what? Buckling. Buckling. You may call it buckling failure. What happens above this, the stress level of the yield stress? What happens in this region? That suppose we look at this way, right? Well, maybe we look at it this way. What happens in this region? It's above the yield stress, so this is what we call yielding failure. And only the green region is what we call the stable behavior. In other words, as a structural engineer, you want to make sure that you're checking your calculation to make sure that your expected stress and the slenderness ratio. Slenderness ratio is coming from your design. Your stress, this one here, is your loading. This thing here is coming from your loading. You can go external loading. And of course, from structural analysis, we talk about different methods, right? There's ASD, there's ARD. For steel structures, you're using the ultimate load, which is PU, remember? And PU is from what? How is PU related to PY? PU is the reduction of reduced version of PY. If it's reinforced concrete, you use a nominal strength, with a PN or MN, nominal moment, nominal force, right? Then you also reduce that to get the ultimate strength. So the way we check it is, first you start with the load combination, determine what is the loading, and you find out what is the working stress and also your ultimate stress. Find these two values. From there, usually these two values should be below your yield stress, sigma y. It should be somewhere here. And your design criterion is to make sure that if you know your sigma, usually sigma u is slightly higher than the sigma, the operation load. So nominal strength is usually higher. So that is somewhere here. You find out these two values. One of them is nominal strength, and the yield strength is usually lower. This is U. Your design criterion is to make sure that you will not choose a slenderness ratio that will make your data point to be outside this stable region. That's how we check it. Okay? So that's how we use this concept to understand the interactions between the loading and also your design parameters. And I believe some of you may have seen this in steel design. Also, you are only provided with some values, and